variant was obtained. So these screening data and the three-dimensional structural data were combined in two small focused mutant libraries, and synthetic genes have been produced from Thermotoga maritima, Thermotoga roseum, Thermophilus, and Geobacillus thermo-olevorans expressed in E. coli. And what we found is that only insoluble inclusion bodies had been found, and that protein folding did not occur in the desired way. So, nevertheless, 18% of the mutants did exhibit synthetic activity for the production of phenylserine, which is this compound without the methyl group here. Yet, as I said before, there was no improved selectivity compared to the wild-type enzyme, and what we actually aimed for in the beginning was to extend the substrate range from glycine to alanine, which is a violet methyl group here. However, none of the mutants did synthesize the target compound alpha-methylphenylserine. We then transferred these results to our partners here in Poland, and they did some in silico experiments in order to increase the stability of the enzymes through salt bridges, stacking interactions, and disulfide bonds on the monomer interfaces. And they generated 11 mutants which had been expressed in E. coli, and they were active, but well, 10 out of 11 were active, but again, there was no superior properties compared to the wild-type enzyme, and also there was no improved stability. What we finally succeeded in was characterization. We did the characterization of temperature stability. It's stable at 37, 60 centigrade. We did the storage stability as well as the determination of the kinetic constant. Here the Thermotoga maritima enzyme showed the lowest or lower Km value. So these are the two enzymes we have been focusing on later on, and in order to shift the reaction equilibrium to the product side, we started with oxazolidinone formation, which is this kind of compound. The advantage of this approach is that we anyhow intended to produce chiral oxazolidinones as chiral auxiliaries as well as chiral building blocks for pharmaceuticals production. So we would in one go obtain the desired product and shift the reaction equilibrium, and as an in situ removal technology. For these purposes, literature tells you to ideally use pressure up to 60 bars and temperature far above 100 degrees Celsius, typically in organic solvents, and these are usually those reaction conditions that are not compatible with enzymes. We therefore switched to protected carbonyls in form of dibutyloxycarbonyl and methylchloroformate. We did see some oxazolidinone formation, but the reaction conditions were too harsh nevertheless, so we had excessive byproduct formation and therefore switched to physical product removal. This was done by, or tested by, ionic liquids. Ionic liquids are highly interesting solvents, also in biocatalysis. Some approaches have been tested, but they have not been established in that extent that would be desirable, although they have very interesting properties. And what we checked is whether the formation of a second phase, which is immiscible with water, could help us in selectively extracting the highly lipophilic phenylserine product from the reaction mixture. And what we found is that in fact we did achieve with 4-BMM6, but also the benzaldehyde substrate was co-extracted, and so we extracted more substrate than product was obtained, and this method failed. The same applies for this approach, liquid membranes, a very interesting technology. You use two liquid aqueous phases with different pHs, and you separate these by a liquid membrane of an organic solvent, the carrier molecule, a neutral one, which is DEPA or aliquot. And we did, in fact, obtain up to 41% of the product on the right side, but here the product is protonated, highly soluble in water, and therefore not further isolable, and therefore lost for in situ product removal, thus not suitable. Zeolite product removal as well. You can design the inner surface and the pore size by changing the silicon-aluminum ratio. What you see here is that benzaldehyde is the preferred compound to be extracted from the reaction medium. That's not suitable, and the same applies also to our microreactors. This is some synthetic foam made of spiraled silicon dioxide, to which the enzyme was immobilized, and we did not exceed 31% even when fresh enzyme was used, and therefore also this method failed. So as a preliminary summary, we can sum up that there was no promising threonine-aldehydes through enzyme engineering. We had no significant improvement through in silico modeling. We did succeed in fully characterizing the tested threonine aldolases. The enzymatic synthesis with amino acid, which are not equal to glycine, failed. The equilibrium shift and in situ removal methods failed as well. So we had to change our strategy and turn over to classical chemistry. The concept we had was in fact to combine these two entities to the phenylserine, threonase aldolase catalyzed reaction. As have been seen, this method failed. And then to submit that to an alcohol dehydrogenase catalyzed reaction, in the course of which the carbonyl is oxidized to a ketone. We have a beta-keto acid which spontaneously decarboxylizes to give the amino ketone, which is then reduced to the chiral alcohol, thereby regenerating the NADH that you need for the reaction. So we have no further requirement for NADH regeneration, we have in situ decarboxylation, and we would have a method to overcome the unsatisfactory stereoinduction by threonine aldolase. Well, it did not work that way. One reason is that the TA did not work, and for this there's another reason I will show you later. What we did after all is to develop a Shaw-Fox method further and modify it, which allows us now to produce any chiral amino alcohol also with branched amino acids, and the drawbacks of the enzymatic room have been overcome that way. Nevertheless, we're facing another drawback also here, because there was no enzymatic decarboxylation. The point is that we needed to decarboxylize this compound, the amino acid, in order to get the chiral amino alcohol. For these purposes, we need a decarboxylase, but there are no decarboxylases commercially available that could help us here. And we then switched to chemical oxidation of this amino alcohol using Swern oxidation. This way you would also obtain a chiral in a keto acid, and this beta-keto acid would spontaneously decarboxylize. So it's the same situation actually as with the ADH catalyzed reaction, but the situation we found there as well here as here is the production of these pyrazines. And well, it was this reaction here with this reaction pathway that led us to the solution. What had happened with the ADH catalyzed reaction, which was much less or was more accompanied by byproduct formation than this one. This is a dead end and therefore not suitable for our purposes. What we did after all is to protect the amino group by butyloxycarbonyl and submitted that to the reaction protocol, and in fact then stereoinduction through the alcohol dehydrogenase catalyzed reaction succeeded, and this is what we got after all: 97% conversion, 98% EE under neutral condition. It has been proven already for equal to 8 hydrogen and here a methyl. We have 5 other compounds currently under investigation, and the results that we have obtained meanwhile are very encouraging. So after a series of failures and drawbacks, we are in a lucky situation to report you today that we succeeded after all at the end of a very long day. So this is what you know already. The lucky news after all, change in strategy was successful. We switched to chemical synthesis of the branched phenylserines. We used a protection method for the amino groups, but biocatalytic reduction was the anchor and the means that successfully helped us to introduce stereo information into the molecules. We got very high yield, high stereo selectivity, better even than we would have obtained using the original concept, using 309 aldolase. So we are in fact in a better situation than ever planned and estimated, and we have now a very versatile process for multifunctionalized beta-hydroxy alpha amino acids. And the message of this 3-year story is stay tuned if it doesn't succeed. And I wish to thank the ERA-IB program as well as the ERA-IB office for funding, supporting us, always having an open ear for our wishes, and our project partners for the very good cooperation in the last 3 years, and you for your audience.
Okay, fantastic. Yes, that's, persistence pays off. Any questions, please, for this speaker?
The question is if you make also the bulk protection of the amino group by biocatalysis, or it was the chemical process?
It was a chemical process, yeah.
Did you try also by enzymatic reaction or not?
Well, bulk protection is usually a chemical process.
I know, but did you try or not?
We didn't. We didn't see the necessity, actually.
I think this could be a really, really important goal of your project.
Okay.
Maybe you two should speak over lunch about future projects.
Yes. Welcome.
Any other questions? No? Okay, you got away lightly there. Thank you. Okay, so get my crib sheet here. So hopefully we will now move one project forward before lunch. Mozaiab, is that correct? Have I pronounced that correctly? Let me just get your project.
Presentation, ERA-IB-2 revised. One on top, further up. No, lower down.
Yeah.
Lower down. That's it.
Yeah. Okay.
Okay. Let me start with thanking all the people from ERA-IB and the national funding agencies for allowing us to study this, well, in many parts, very surprising project. The project was full of surprises, and I want to tell you the story, what this project is all about. Well, we had a consortium consisting of groups from France, 2 groups from France, 1 group from the Netherlands, 1 group from Finland, and 3 groups from Germany, 1 in Tübingen, 2 from Dresden. And the aim of our project was to learn about the biosynthesis of this compound, which is called astin. And these astins have anti-tumor activity. And the problem with these astins is that they are only available in very low amounts. They have to be extracted from aster roots, from plant roots. And you need a few kilograms of the roots to obtain a few milligrams of the compound. So what we wanted to do is we wanted to detect and clone the genes, to express them heterologously, and thus produce, by combining the genes in clusters, to produce more of the astins, and then to analyze whether these astins have other biological activities in addition to the anti-tumor activity. Now, these are the aster roots which are used for extracting the astins, and they're also used in Chinese medicine for making tea, and this tea is supposed to have a lot of biological activities, be active against coughs, and not just anti-tumor activity. And what we did was we could detect astins for the first time in fresh plant material. Before that, it has only been detected in these roots, but we could show that it's also present in fresh plant material. And what is very important with these astins for the anti-tumor activity is that they are cyclized and that they contain these 2 chlorine atoms. Without the chlorine atoms, they have no anti-tumor activity, and the linear molecule doesn't have one either. Then, if you want to identify genes, biosynthetic genes from plants, you have a problem, because in contrast to bacteria and fungi, where in most cases the biosynthetic genes are clustered, in plants this is rather unlikely. So this would have meant that we have to try to detect all the individual genes involved in the biosynthesis, one by one, and then stitch them together. But there is a similar compound to astins called cyclochlorotoin, and you see you have the same non-proteinogenic amino acids as in astins, but this compound, this fungus, was isolated from spoiling rice, and the cyclochlorotoin are toxic compounds, hepatotoxic compounds in contrast to the astins. So our idea was now to find the genes from the cyclochlorotoin biosynthesis in the fungus, and then use them for detecting the genes in the plant, because we assume that the enzymes involved, and thus also the genes from cyclochlorotoin biosynthesis, should be very similar to the ones involved in astin biosynthesis. And it would be much easier to work with the fungus. So what we did is we decided to sequence the genome of the fungus, and we obtained a sequence, but due to patent reasons, I cannot show you the sequence, but what I can tell you is candidate genes are present, but they are not all clustered. But at least we have the genes, so now we could start to look in aster, in the plant, for the corresponding genes. What we can say is that, for example, if we have a non-ribosomal peptide synthesis, which we can assume from the structure of the molecule, that for cyclization we need a CIT, a condensation, terminal condensation domain. So this would also help us to identify, to distinguish between several non-ribosomal peptide synthase genes.